Okay, hello everyone. Today's session is we're discussing first op redundancy protocol concepts. That is module 9. And basically, this module introduces the redundancy protocols, which will deal with failure of default gateways, if I can say of a single default gateway router, which can potentially cut off all external communications um, from within a LAN. So when we talk of redundancy protocols, I think we are now familiar with what redundancy is. And in this case, we're discussing redundancy on default gateways. I think by default, every local area network has a default gateway, and I think it's only one. We've only learned how to configure one default gateway on a given LAN. So every host we have one default gateway. But what happens if we lose connectivity to that default gateway? It then means all devices on a given local area network, they no longer have connectivity to the outside networks, basically. So the redundancy protocols, the first of redundancy protocols provides for redundancy for gateways. And we'll take a look at basically how that happens. Right. Uh, Objectives, topic objectives, we'll explain the purpose and operation of first of redundancy protocols, then as well as explain how what standby redundancy protocol operates. Okay, default gateway limitations. So end devices are typically configured with a single default gateway. If the gateway router interface fails, LAN hosts lose outside LAN connectivity. In this occurs, even if a redundant router or a layer 3 switch that could serve as a default gateway exists. Redundancy protocols are mechanisms that provides alternate default gateways in switched networks where two or more routers are connected to the same LAN. Right, so the redundancy protocols, what they basically do is solve a situation where we have a single point of failure for our default gateways in this case. They allow multiple routers. They allow multiple routers to share what we call a virtual IP address or a virtual MAC address. So instead of having one default gateway on one router, we have what we call a virtual IP and a virtual MAC. A virtual IP and a virtual MAC is formed when we have a group of routers, which are obviously enabled to offer services provided by the redundancy protocols. So a group of routers, instead of one, they will share a virtual IP and a virtual MAC address. And if one of the default gateways, the one which is active, fails, then another router, another interface, provided they're in the same VLAN, takes over. So basically, that is what the first open redundancy protocols speak to. Uh, Maybe if I can explain it a little bit better, the chance that diagram. So you can see this PC when we are configuring all this while when we're configuring PC, the IP addressing for a given host, there's the IP address, there's the default gateway. So there's IP then there's a default gateway. Default gateway in this case, Ratoya said it was of this interface, right? However, if default gateway already fails, even if you can see Panama redundant links, you can see there is another redundant link irrelevant. Okay. So a redundant link is there. However, kuti tichibude network, outside the network, we will need the default gateway of this interface here. But since we configured default gateway for this interface app, we don't have a way of actually offering redundancy for my default gateways. So we can have my redundant links, so redundant paths that can lead us to different, I don't want to say different networks. We can have redundant links, different pathways. However, kana default gateway yedu yachinja, our hosts, they don't have a way of changing this default gateway. So even if we have redundant links, we don't have a way of changing this default gateway. That's where the first hop redundancy protocols come in. So what they basically do is, in this example, you can have these routers. You can have, for example, these two routers, provided they're in the same VLAN, the interfaces that you're going to be using, they're in the same VLAN. So for example, you can see even from the addresses I pop up, 10.1, 10.2, 10.1, 10.3. It means they're in the same IP subnet. Same VLANs also means same IP subnet. So provided interface ERI and interface ERI, they're in the same VLANs, or any other interface on those routers RN1, R1 and R2, then we can configure them to act as a group of routers with a common virtual IP address and a virtual MAC address. So here, instead of configuring the default gateway of a given interface, we configure the default gateway of this virtual IP. Now, between the two, one will be acting as an active router, the other one will be acting as a standby. So let's say if this one is the active, when it fails, here the virtual IP just changes who controls it. If this one is active, then R1 is controlling this virtual IP. Processing, forwarding of and routing basically is going via this R1. And if this link fails, then this one will become backup, and now it will be in control of the virtual IP. And in short, that is basically what the first hop redundancy protocols are. And I think this is a very short module. Right. Router redundancy. One way to prevent a single point of failure is to implement a virtual router. To implement this, multiple routers are configured to work together to present an illusion of a single router. So the illusion here is being presented by the virtual IP. So what the hosts see is the virtual IP in the virtual MAC address. So even if there are changes within the group, if one router fails, another takes over, the host is sort of, it doesn't see that. To the host, everything is transparent. It does not see if there are any changes that are happening within the group. The IP address of the virtual router is configured as the default gateway. Okay, when frames are sent to the host, from host to the default gateway, the host uses FHRP to resolve the MAC address that is associated with the IP address of the default gateway. So in this case, this resolution, what we are basically using, instead of using the physical interfaces of our routers, we are using the virtual IP and the virtual MAC. So in terms of resolution, address resolution, what will be used for resolution are these two addresses. So you forget the physical interfaces of the participating routers in a given group. What you'll be dealing with now are the virtual IP addresses. A protocol is used to identify two or more routers as the devices that are responsible for processing frames sent to the MAC or IP of a single virtual router. Hosts send traffic to the address of the virtual router. The physical router that forwards this traffic is transparent to the host devices. I think we've gone through this. A redundancy protocol provides the mechanism for determining which router should take the active role. Right, so where does the protocols come in? Protocols are exchange of messages. Where does the protocols come in? So in a given network, you have two routers. They will need to exchange messages between them. So, for example, they know which of the two routers become the active router and which becomes the standby or a backup router. So there is an exchange of messages for that. That's where the protocol comes in. Now, protocols also have the function of determining what happens if the active router fails. Now, let's say we have three routers. If we have two, then you might assume automatically the second one gets the role of being active if the current active fails. However, if we have three, then there will need to be a choice between these two, R2 and R3. Which one takes over? Protocols are responsible for um, selecting which of the two routers gets to play the role of the active route. So basically, that is where the protocols come in. And we have mainly two protocols I think we are going to discuss. It's actually one. So the word standby redundancy protocol, then we have the other one, FHRP. This one being a Cisco proprietary, and this one being an open standard. So like always, I think you've seen a trend. You could see Cisco always have proprietary protocols. I think Packet Ether channel, one of those two was Cisco proprietary as well. My discovery protocols, Cisco in a proprietary. I think there are quite a number of protocols where Cisco has proprietary protocols for, in those given instances. All right, steps for router failover. When an active router fails, the protocols transition the standby router to the new active router. The steps that follow: one, standby router stops seeing hello messages. Then the standby router assumes the role of forwarding router. Because the forwarding router assumes both IPv4 and MAC addresses of the virtual router, the host device sees no disruption in the services. Right, so like I was saying, this is one of the functions of my protocols. There is an exchange of messages in Etica so that we can determine uh, where when the standby router comes in and becomes the active router. So in case of a router failover, number one, we have loss of hello messages. Okay, number one, we have loss of hello messages. So you're going to realize there is an exchange of messages that is happening between or not all between routers that are in the virtual in the virtual group. They are sending each other hello messages. Hello messages every depending on the protocol. For example, for HSRP, By default, every 3 seconds, there is a message which is being sent. That message contains information of the priority, for example, the priority of that router. The priority which will then be used in election process, for example, to choose which one becomes the active router or which one becomes the standby router. So every 3 seconds, a message is being sent. So between two routers, for example, or let me say in this example where there are three routers, they are exchanging messages, hello, are being sent every 3 seconds. Now, in the case of failure, if this one fails, it stops sending hello messages. In the moment these two realize my messages are chawuya, that is where the failover process starts. My messages are chawuya. We have what we call the dead timer as well. So we have the hello timer. We also have what we call the dead timer. I think in this case, dead, this is hello. Dead timer is times 3, 10 seconds for FHRP. So if the standby router doesn't get uh, 3 consecutive hello messages, if it doesn't receive 3 consecutive hello messages, then it knows the active router is now down. Then router failover process, it has to start. So point number one, we have the loss of hello messages. Then we go to number two. Number two, this is where the standby router takes off. Standby takes over. My message is my hello, they've stopped coming. Standby router takes over and assumes the role of the active. In this case, standby router ndora kucontroller the forwarding and routing in that virtual group. Ndora kucontroller the virtual IP, ndora kucontroller the virtual MAC address as well. Then lastly, we have seamless connectivity. Even if default gateway radio on a physical interface is down, we still have connectivity because of the first hop redundancy. Typical questions we get, these numbers will be very important. I think I also know for the other one, FHRP. For this one, we have, it is less by default. The yellow time is much less, 1 second, and the dead time is 3 seconds. So if you look at these timers, the yellow timers and the dead timers, what it basically means is this protocol is very quick to react kana paita failover, paita router failover, because after 3 seconds, router action, because that's the dead time. After 3 seconds, ring router detector, which is the active router is down, therefore the standby will take over. This one, after 10 seconds, a lot can happen in 10 seconds in a network. My users, my one auto complain that we don't have connectivity. So you see, these values can be manipulated. We can change them depending on what you want in your network. If you want quick reactions to changes that are happening in the network, then you definitely need to reduce these values. The timers are. Here we have a comparison of the options we have for the redundancy protocols. Number one, we have HSRP, which is the Cisco proprietary protocol. Right, this one makes use of active and standby routers. So we have one active, then we have another standby, then we have other routers in the group. So it makes use of the active standby mode. All hosts in that network, they are configured with the virtual IP. I think is like every other redundancy protocol. So my hosts, they are not configured with the physical IP address of interfaces. They are configured with the visual IP. Then we also have the active device is the device that is used for routing. We've gone through that. The standby device takes over. Then we have, or when preset conditions are met. Then we have something missing here. Preempt. There is something to do with preempt. When enabled, if one router fails, then another one automatically comes in. Preemption, let me put it this way. So I have two routers. This one, it has higher priority. So let's say this is R1, this is R2. So this one, it is the higher priority, meaning it becomes the active router soon as we put up my router's ADS. So this is our group. Now, when we talk of preemption, if this one fails, then this one takes over. But what happens if this one recovers? Here we are now using this one as the backup, as the standby. But if this one goes back online, what happens? So if preemption is enabled, the higher priority rikaenda back online, rinofanira kudzoswa privileges equal the active router. Because most of the times, it's a choice you have to make as probably an administrator or engineer. This router is very capable to control a network here. Probably the hardware, in my latest features, the hardware, it offers more bandwidth in a processing power yakawanda. So in a case yekuti probably yangoita problem, then another router with less processing power, less effective hardware can take over. But would you like that to continue in a functioning network? Probably not. So panodzoka a more functional router online or it recovers, there should be a process yekuti idzokere ite active router. That process do you know the preemption. So most of my redundancy protocols ane that feature which allows higher priority routers to take back my privileges ekuva the active routers. Right. Then we talk of FHRP for IPv6. This is just another version for version 6. So this one, it was for version 4. This one is for version 6. There is not much difference between those two. It's still the same functionality. It's still the same visual IP, visual MAC addresses. Here, with IPv6, obviously, we now have a link local address. So there's a visual link local address, there's a virtual GUA, there's also a virtual MAC address. So the group will be using this as the virtual addresses. Then we have the virtual router redundancy protocol, non-proprietary. That's an open standard protocol. Multiple vendors can use that one. Also use the same concept here, virtual IP address. Not much difference. I think the difference between that one and the FHRP in a proprietary number one, my default timers number two. That one uses active and standby mode. The VRRP uses it should be master and backup. Yeah, when the master fails. So this one uses master and backup. But I think the working principle stays the same because there's a group of routers which create a virtual IP, and basically that's it. The version 3, this is an equivalent of for IPv6. If you want to provide redundancy, default gateway redundancy for IPv6. Then you use version 3. This one is for version 4. We also have gateway load balancing protocol, another Cisco proprietary redundancy protocol, which also offers redundancy for default gateways with an additional feature of load balancing. Right. I think when we discussed Ether channel, we talked of load balancing. In this case, two more routers in a group. I have my LAN here. Let's just have a LAN. Let's have a LAN. Right. So with the redundancy protocols, with the first hope redundancy protocols that we've discussed, HSRP, what is happening is it's only one router which is functional within the group. So this one is the one that is active during is functional. So all forwarding within the group in through one physical router. Then if it fails, another one takes over. There is no element of load balancing there. Load balancing basically means all of them, they sort of act as if they are active. So if traffic is being sent and this one really overloaded, if I can say, then in the traffic on the other route. That is basically what the other protocol, the gateway load balancing protocol does. So it offers both. It offers a gateway redundancy by creating the virtual IP. It then also offers load balancing. Instead of only having one active router forwarding all the traffic, it has all the devices, all the routers in the virtual group performing the role of forwarding. All right, then we have gateway load balancing for IPv6. That's an IPv6 equivalent. The last one is ICMP router discovery protocol. It allows hosts to locate routers. So this one is not a redundancy protocol per se. This one is a discovery protocol. Yeah, the good thing is a legacy protocol, meaning it's no longer in use that much. Actually, it was replaced by ICMP v6. So this is the protocol that was replaced by ICMP v6. Making use of RA and RS messages. That's how we can discover routers within a given network. So the last one, EO, is not a redundancy protocol per se. Not sure why it's there, but we move. Now we go to the HSRP overview. So the whole standby redundancy protocol, I think we've touched on this a little bit. It's Cisco proprietary one. It makes use of a virtual IP to provide first hop redundancy. It makes use of the active and standby mode, meaning we have an active router, we have a standby router. We've gone through that. We have a VIP and we have a VMAC, virtual IP address, and a virtual MAC address. The function of the HSRP standby router is to monitor the operational status of the group and to quickly assume packet forwarding responsibility if the active router fails. I think we've gone through this already. So HSRP, everything we've said about the first hop redundancy protocols, just add Cisco proprietary at the end, and you have HSRP. Priority and preemption. The role of the active and standby routers is determined by the election process. By default, router with the highest IP address is elected as the active router. However, it is always better to control how your network will operate under normal conditions. Right. I think I've touched on this a little bit. Like in a production network, it's not always wise to say router in the highest IP by default uh becomes the active router, because router rinogona kuita highest IP rinogona risiro router really powerful in your network. So it is very wise kuti router capable, rine hardware capable in your network ndo rinofanira kuita the active router, so that all the forwarding, all the routing, all the processing of our packets go through that one. So to control how that happens, then there is what we call my priority values. My priority values, maybe they go from 0 to 255. I think the issue to do with priority, Shiona Pagato one day, I think STP, we talked about priority, OSPF, we talked about priority. There is quite a lot of protocols in terms of these priority values. So my values either go from 0 to 255. For HSRP, the default value is 100. And if my priority is either they are equal, then we go to use my IP address. So if we sort of control the process, we configure my priorities on my interfaces edu. And I think this is the command standby priority interface command. So you configure my priorities edu. Highest priority becomes active. So router that you prefer cultivate active router, you configure it with priority 255. Then basically that's it. That's how you control the election process. So panosend my hello packets, do panoshow information negative, my priority value is 255. Then the other one, my priority value is 0. And obviously, after that exchange, 255 in donors are consequent the active router. If the priorities are equal, the router with the numerically highest IPv4 address is elected. Okay. I think we touched on this already. We're good. Yeah. Uh, Preemption continued. By default, after a router becomes active, it will remain the active router even if another router comes online with a higher priority. All right, this is default. By default here meaning no preemption. This is default. So this is default for our routers. By default, we don't have preemption, meaning even if a router in a higher priority comes in, it doesn't automatically becomes the active router, or it doesn't even trigger the election process. You could consider the active router. However, if we enable preemption, and that's the command, the standby preempt interface command. If we enable preemption, it then means if a highly prioritized router comes in online in our network, in our virtual group, then it triggers an election process. Election ikaitika, then in a higher priority becomes the active router. And basically, that is what is here. You should be very careful with default. By default, we don't have preemption. Then if we enable preemption, routers with higher priorities coming online triggers an election process. Preemption only allows a router to become active if it is higher priority. Okay. With preemption disabled, the router that boots up first will become the active router if there are no other routers that are online. I think this is simple to check in. HSRP states and timers. So, and times, states and times. So, our states in summary, we have the initial, learn, listen, speak, standby. The initial states, this is when our interface is coming online and it's not participating in any election processes. So this is the initial state. Interface ready. When you enable an interface, that's the initial state. The LAN state, this is where we are discovering the virtual IP. Router ready, router the VIP. So at the LAN process, at the LAN state, we are basically trying to discover the virtual IP. And in a case where router radio doesn't learn any virtual IP, then obviously Ndorno validator, the router no provided the default gateway because there is no other router, there is no other router in there, so there is no group share. Automatically, router, if it does not learn anything, then it will become the active router. Listening, in the listening state, we are now listening for hello packets. We are now listening for hello packets. So here at this stage, we now know the VIP. Here we are learning. Here we now know the VIP. And we are now listening to hello messages. However, no hello messages are being sent. So listening, we receive, but we don't send. No messages are being sent, but we listen. Speak. The speak state, here the router is now actively participating in the election by sending hello packets. Here, takuisawo voice redu kuti tikwanise kunzwikwa, kuti tikwanise kuitawo the active router. That is the speak state. Then the last one, the standby state. Here, it's a state which is designated to a router which will act as a backup route. And basically, I think we talked about this. Yellow packets, 3 seconds, 10 seconds dead time. You can lower these timer settings to speed up failover or preemption. However, to avoid increased CPU usage, do not set the yellow timer below 1 second. So lowering that timer, it means you have faster failover process. However, it means my yellow annoya every second, so load processing power here, my devices will need to be very strong. And basically that's it for HSRP. I don't think it's a very big module. Done.